Welcome back. In the last session, we have discussed the pharmacokinetic pharmacokinetics of the drug discovery process, and now we will discuss the what is the one of the very important aspect of drug discovery process. Although it appears to be little empirical, whatever we will be talking about now, but still these empirical things are useful, like Lipinski's rule is empirical, but it helps. So, many empirical rules are there which are actually derived out of the whatever the experimental results. There is no basis for that, means mathematical derivation for those empirical rules, but they are useful. You cannot discount them, and one of them in drug discovery process, apart from the Lipinski's rule, is this quantitative structure activity relationship. Now, what is and which is quantitative structure activity relationship? This is activity relationship. QSAR. The QSAR, what is the means what they try to do in QSAR? They try to formulate something where the activity of a drug is equated by a formula to the parameters which one thinks that they are very important for the drug to be active. Okay. That means, what we are trying to say, that activity of a drug as a function of parameters that one thinks that they are important, and whether you can connect that to the activity. It is like, say, if I give if I see an organic a molecule, and if I ask what will be its chemical activity. See, here activity means the biological activity. We are not talking about chemical. Okay. Biological activity. Chemical activity, what we do? We look at the functional group and then we will say that okay, this functional group is present, so it should give this type of reaction. Okay. In case of biological, still is very difficult to have an equation, although as in computation, what happens? You have different molecules and you tell which molecule will react which pathway, the other molecule will react in another pathway. So, there are ways to define the activity, chemical activity of a molecule by computational means. That has progressed rapidly in the last few years, because of high power of the computation. In case of biological activity, the situation is more complex, is more complicated, complicated, but that is why still we are in the age of this empirical rules, because the situation is so complicated. So, ultimately through various experimental results, you come up with some kind of an equation. Okay. Like I can compare this with Woodward's diene rule of calculating the lambda max of a diene functionality. Now, what is the basis of that? There is no basis, because he just checked all the UV maxima, lambda max of various compounds, and finally, he came out with that okay, if it is a homoannulation, I think if it is some additional double bond, substituent, all these are basically empirically done. Hetero, I think that was heteroannular and homoannular diene, and that has got a base value. So, it is very similar to that. Now, the first question is, how do we express the biological activity? Because so far as we are concerned, up till now biological activity was basically defined. There is no particular terminology, it is very difficult. No? Biological activity is going against different targets. So, what people have decided that better do this, because you know IC50 values, you know these different parameters, IC50, ED50, effective dose, all these things. So, biological activity is expressed as a logarithmic term log 1 by C. C is the concentration needed to have the desired effect up to a certain extent. Now, it is up to you whether you take the concentration needed to achieve 50% of the 50% of the effect, or you fix it at 90% or you fix it at 70%. Basically, concentration needed to have certain extent of the desired effect. Okay. Now, why you are taking C 1 by C the reciprocal? Because we know the more concentration, the higher the concentration which is necessary to have the desired effect, that means the poorer is the activity. So, it has got a reciprocal relation. So, that is why 1 by C people have taken, and usually these activities are dependent on parameters, they usually follow some logarithm plot. It is not a direct relationship that activity is proportional to the say hydrophobicity. You cannot have that. Okay. So, that is why I think that with that aim people have on the biological activity side, that means on the y part. See, in a equation you have a x part, a linear equation, and then and y part, something like this, if it is a linear. So, y here is log 1 by C. So, we know why it is 1 by C and why it is logarithmic, because there cannot be any direct relationship like that. Now, what could be the parameters? Now you have to identify the parameters. One has to be P, the hydrophobicity or lipophilicity, because what happens if it is extremely hydrophobic, if it is extremely polar, suppose, okay, the other way around, it is extremely soluble in water. Then what happens, as the molecule goes inside the GI tract, see, that is mainly water with different pHs. So, the molecule will remain in the water, it will never be absorbed. So, that is the problem. On the other hand, if it is extremely lipid soluble, then it will remain in the membrane, because the membrane is full of lipids. So, basically the membrane will solubilize that molecule. So, it will not come out or it will not go inside. So, those are the problems. So, one is basically I can say that this biological activity is dependent on P, that is the whatever it is a hydrophobicity index. What could be the other parameter? The other parameter is that apart from P, you can have electronic parameters. Why electronic parameters? Because electronic parameters definitely part out the chemical reactivity of a molecule, that we know, like benzoic acid versus paranitrobenzoic acid, which one is more acidic, you can tell from your organic chemistry knowledge. Similarly, here also we can say that, because I told you that that balance between the ionic form and the neutral form, that is very important. How much is the percentage of the neutral form, how much is the percentage of the ionic form. So, those are that can be parted by the electronic property of the molecule. So, there has to be an electronic parameter on which the drug the biological activity will depend. Okay. So, now we have identified P as the hydrophobicity index or a hydrophobicity parameter. There is an electronic parameter, and there is a third one, that is called steric parameter, because if the molecule is too large, then it will not reach the target. So, if it is sterically highly crowded, then there is a problem of reaching the target. So, these are the three parameters, the minimum three parameters. See, there are other parameters also that is possible, but we are just, because for this course I think we will just stick to these 3 parameters, and we will just discuss how these parameters are evaluated. See, one thing you must also know, that suppose I have a lead compound which is represented as, suppose a benzenoid compound, I do not know, so let us put some carboxy group here, some see, suppose with some adequate length, a carboxy. Suppose I find that this molecule is having some property against the target. Okay. So, then what is usually done? Optimize the lead. You have to optimize the lead. That means, you have to put different substituents in different position of the molecules. Okay. Now, suppose I put an R1 here, okay, and another substituent R2 in the same benzene ring. Now, R1, the question is, are you going to make, say R1 can be methyl, ethyl, propyl, butyl, this R2 can be also different groups. Are you going to make these molecules and then try to find out its activity, or is there any way to predict that what will happen if I have a methyl versus say a methoxy or a nitro, what is going to happen? That is why this quantitative this QSAR model is so important. So, without making the molecules, you can, because there is a database now that this type of molecule has this type of hydrophobicity, and if you put a methyl group, the hydrophobicity will increase that much. So, you can have a huge database, and from there you can calculate what will be the hydrophobicity of a molecule without making it, okay, without making that. And everything is like that, electronic parameter. There must be something which without making the molecule you can predict what is the value of this electronic parameter, what is the value of the steric parameter. Okay. So, that when you connect all this, then you get the biological activity, because biological activity, now I can say that biological activity will be some constant into hydrophobicity plus some constant into the electronic parameter plus some constant into the steric parameter and plus the C factor, that is y equal to m x plus c. So, that has to be at the end. Okay. So, let us take one by one. What is the hydrophobicity index? We know that this is done in octanol water system, okay, because that is very close to whatever our membrane constituents are. The environment in the membrane is close to the octanol in octanol water system. So, that is you get the partition coefficient. Now, this is what is partition coefficient. Now, people started taking drugs of belonging to the same class and then determining the partition coefficient, okay. And they then equated this, that log 1 by C I told, that is the biological activity. So, initially they just disregarded the electronic and the steric effect. They only thought that only partition is the actual factor that will decide the biological activity. So, they had some kind of reaction like this, log 1 by C equal to minus k 1 log p plus k 2. Okay. Now, what they found later on, that these formula will only hold good if the molecule is only targeting the membrane, because the membrane where this question comes, the hydrophobicity, hydrophilicity, where it is coming? It is coming mainly the question of crossing the membrane, which is a lipophilic membrane, right. So, usually this type of formula holds good for CNS active, that means the anesthetic drugs. The anesthetic drugs, what they do? They actually go to the membrane and then ultimately affect the central nervous system. So, this formula holds good for those type of molecules, and it is written here that a straight line relationship between log p and biological activity is observed in many QSAR studies, but only having a limited range of log p values, which is relatively narrow. That means, a narrow range it holds good, but if you have a wide spread, say your log p value is, suppose some log p value, some molecules you have different molecules A, B, C, D, E. Here the log p is 1, here the log p is 2, here it is 3, here it is 4, it is 5. This is a very wide range of difference, because remember this is log. Okay. So, it is a huge range, and for that this linearity does not hold good. Linearity holds good only when, say, A B has 1.01, this is 1.02, 1.03, like that, then only this type of formula holds, otherwise it does not hold. And I will show you that actually what is the nature of curve if you start plotting log 1 by C with log p for different, is a very wide spectrum. So, the curve goes like this, that it reaches a maxima and then so it is a parabolic curve, and then you have a maximum. This is what is called the optimum log p value. Okay, the optimum log p value. Now, if you take a very narrow range, suppose up to this point, so it is almost linear. So, in that case that formula will hold good, but actually the formula should be like this, it should have a square term now. Log 1 by C, what they did, put earlier it was k 1 log p minus k 1 log p plus some k 2. Now, they put another term k 1 log p square minus. Okay. So, what happens that, see, this can actually explain this type of curve, that log p square term has a minus sign in front of it. When p is small, that means log p square will be very small at that time. So, you can neglect this log p square term. So, it will basically it brings the earlier formula, but as you, this represents the first part of the graph where activity increases with increasing p, but when p is large, log p square term is very significant and eventually overwhelms the log p term. See, it is decreasing at that point. When log p is very high, that means this term will predominate at that point. So, the whole thing becomes negative. Negative means it is going down now, downhill. Okay. So, this is actual the case, that is about the log p. So, there cannot be a very simple formula like that. It is only if you are only tackling a small subset of molecules where the log p values are within a very narrow range. Then came the substituent hydrophobicity. Substituent hydrophobicity is basically that, suppose you have a benzene molecule and you have a substituent X. Okay. Now, if you want to assign, see, this is very useful in the sense that if you know the hydrophobicity index of substituents, then what happens, you can measure the hydrophobicity of benzene, that is a common item. Okay. So, if you know the substituents hydrophobicity, then you can add all these. If I have, say, hexamethyl benzene, what will be its hydrophobicity? If you know the hydrophobicity of methyl and if you know the hydrophobicity of benzene, you can tell what will be the hydrophobicity of this hexamethyl benzene. So, basically now you have a substituent where it says that now it is denoted by pi x, that means pi x is basically what will happen, pi x will be hydrophobicity of this molecule minus the hydrophobicity of this molecule. That means, the benzene hydrophobicity is subtracted off. The hydrophobicity of this is what? It is assumed that hydrophobicity of this is basically hydrophobicity of benzene plus hydrophobicity of X, okay, minus hydrophobicity of benzene. So, what will happen? That will give you the hydrophobicity of the substituent itself. So, like that. So, basically when several substituents are present in a system, what will happen? The overall pi, that means the hydrophobicity, will be the if you have to add the different substituents, whatever, how many substituents are there, what is their hydrophobicity index of various substituents, from where the substituents hydrophobicity index were evaluated, that is by making simple compounds and then get a database that this is the hydrophobicity index of methyl, then nitro, then carboxy, all these are now known. Okay. So, suppose I want to know the hydrophobicity of chlorobenzamide, say suppose chlorobenzamide, CONH2 and chlorobenzamide. So, what will be its hydrophobicity? It will have the log p value of benzene plus the pi of, pi means this the parameter, the parametric hydrophobicity. So, CONH2 hydrophobicity and the chlorine. Okay. So, it will be log p benzene plus pi Cl plus pi CONH2. Now, these are known because you can make benzamide and chlorobenzene and you subtract that from benzene. So, you get the substituent hydrophobicity, and so it will be 2.13, chlorine has 0.17 and CONH2 has minus 1.49. Okay. So, now you add all these, you will get 1.35, and what is the observed? If you can make this molecule or you can buy this, you just do it in partitioning between octanol and water, you see this is 1.51, which is not a bad matching. Okay. So, you have some idea of the hydrophobicity, and this is another example 1,3-dimethyl benzene. I told you about hexamethyl, this is 1,3-dimethyl. So, that will be what? Benzene plus the hydrophobicity of 2 methyls. So, that is for 1 methyl it is 0.56, for 2 methyls that will be 1.12. So, that will be 1.12 plus 2.13. So, that will be 3.25. No? And what is the experimental value? See 3.20, very close. Now, this is what is called C log p. Now, they have put a term C. See, log p means, this is also important, log p means experimental value of this hydrophobicity. C log p is the calculated, that means without doing any experiment, that is why you have this C. So, C log p is the calculated one. Okay. So, that is all about the, so we have P and we also have individual substituents hydrophobicity. Now, let us see what is the contribution from the electronic effect, because we realize that biological activity has to have some contribution from electronic effect that is operating in the molecule, because there will be lot of weak interactions which are controlled by this electronic effect. Now, electronic effect, the question is how do you measure the electronic effect? Now, the electronic effect has been measured in organic chemistry, organic reactions by none other than a person whose name is Hammett. Hammett is a very well known figure in organic chemistry. So, Hammett substituent constant, Hammett parameter, okay, that is a measure of the electronic effect sigma. Electronic effect is denoted by sigma, individual substituent hydrophobicity by pi, the overall molecule is basically log p, and so we will come to the steric factor as when it is come I will tell you. So, now this substituent, this electronic parameter, how do you calculate that, quantify that? What Hammett did is that he took benzoic acid, okay, he took benzoic acid and then put a substituent in benzoic acid and then determine the dissociation constant of these two acids, okay, and took a, that means it is basically log Kx, Kx means this compound minus log Kh. That means, when there is no only there is hydrogen and when there is substituent. So, you take the difference of this dissociation constants, and that will give you the electronic parameter of sigma. Because you know that if it is electron withdrawing nitro, then what happens? This will dissociate more. If it is electron donating methoxy, dissociation will be less, that we know. Like benzoic acids containing electron withdrawing group substituents will have larger Kx values, they will dissociate more than benzoic acid itself, and therefore, the value of sigma x for electron withdrawing substituents will be positive, and for substituents which are such as Cl, Cn, CF3 have positive sigma values. Okay. So, sigma is basically you take an acid like benzoic acid, and then substituent effects are basically you take the difference between the two log of the dissociation constants. Okay. And finally, the steric factor. The steric factor was given by Taft, another scientist. See, Taft is the one who gave the steric factor, how to calculate the steric factor, okay, or how to quantify the steric factor. And now, the steric factor is denoted by Es. Okay. So, if it is denoted by Es, question is how to quantify Es. So, what he did, he took this he took say CH3 COOMe, a methyl ester of ethyl acetate, and then substituted this methyl with different substituents, okay, and then check the hydrolysis, the rate of hydrolysis of these esters. Okay. Now, you know the hydrolysis means saponification. Say esters can be hydrolyzed by acid or by base. If you do it in base catalyzed, in saponification, the formation of the tetrahedral intermediate is the rate determining step, OMe, right. So, these are the two intermediates. Now, these intermediates will be sterically more crowded, because you started with sp2 carbon, now this is sp3. So, the more steric bulk it has, the less will be the rate of hydrolysis. So, that is the way you can quantify the steric factor. So, basically it is nothing but the difference between the two rates of hydrolysis. Again it is Es equal to log Kx. Now, this is rate. In case of the electronic factor, that Hammett's electronic parameter, that is the equilibrium constant, this or the dissociation constant. Okay. That is dissociation constant. In this case, it is the rate, because steric factor is associated with rate. So, this log Kx, that means the rate of hydrolysis of this minus the rate of log of the rate of hydrolysis of the parent compound. Usually, the parent compound is H, because they put hydrogen, because that is easy to do that. Very easy to if hydrogen is the reference, then in the books it is said that you can take any reference, that is true, but it is better that you take hydrogen as the reference, like in earlier the Hammett equation, the same thing has happened. So, now we have idea about these three parameters, okay. The hydrophobicity, that is given by log p, usually that is called C log p, because that is a calculated one, all are calculated. Then you have this sigma, and you have this you have the steric factor Es. So, what will be the final equation then? The final equation will be something like this. Log 1 by C is the biological activity. So, that will be directly connected to log P, and there will be a constant in front of it. Then plus K2 into sigma, sigma is the electronic contribution to the biological activity, and then this is the steric contribution to the biological activity. The contribution maybe could be in the negative sense, it could be in the positive sense, okay, both, and finally a constant K4. So, this is what is called Han's equation. Okay. Now, you can use pi also here, k 1 pi. If you have substitute, you can, lot of people have used, if you have a suppose compounds A, B, C, D and they are differing only in substituents, then you can use pi here. Okay. Only the substituent hydrophobicity can be used here. Okay. So, there are different variations of this Hanske equation. You can make it more accurate by doing that 1 by C is equal to say minus k 1 log p square plus k 2 log p plus k 3 sigma plus k 4 steric plus k 5. That means, you are having more accurate description of the hydrophobicity. I told you about this equation. Okay. So, that is the actual one. So, you can now, for all practical purpose, you can remove this, but if you want to really rigorously quantify the biological activity, then maybe you can use this formula. But remember, this is empirical formula, but this gives, the pharmaceutical companies use this QSAR equation and then try to figure out, before making any molecule, try to figure out what is the prospect of the biological activity, whether it will increase or it will decrease, because now you have all these, you cannot just, it does not only depend on the log p, it depends on sigma. So, if you increase the hydrophilicity, your lipophilicity, what happens to the sigma, that also you have to take care, what happens to the steric effect. Okay. So, all these combinations will ultimately tell you that the potential, it is not accurate, but the potential whether you are going in the right direction or you are going in the wrong direction, you are going to make the molecule or not. Because after all, to test everything you have to synthesize the molecule, and that costs energy, that costs money, and that costs human resource. Okay. So, or that involves human resource. So, that is why they are extremely careful that they do not want to spend money on something which is bound to fail. So, they do this Lipinski, then they check with the Hanske equation that whether there is a prospect of having good activity of the molecule by using this equation. There are many modified equation, I tell you. Hanske equation has now, because of the different parameters are there, you can calculate computationally also. So, there could be say surface electrostatic potential, that could be also an important criteria to be put into this equation. We are not, instead of having this sigma, because sigma is very specific, benzene and then the substituents, dissociation constant, but computation can give you the surface potential, what is the charge density at different in the contour of the molecule. So, you can have different variations of this type of equation, but this was the original equation that was given by Hanske. Okay. There may be modern versions of this, but we are not, our purpose of this session is to just to know that what is QSAR and what are the parameters, minimum parameters that one needs to consider in order to quantify, semi-quantify, I can say, quantify the activity, biological activity of a drug. Okay. So, that takes care of this QSAR principles and its how it came about, how it is arrived at. Okay. Thank you. We will take one more class possibly, and that is where we will discuss various problems on the topics that we have covered under the biochemistry section as well as under the medicinal chemistry. Maybe one or two lectures are required to discuss those issues, and many of these issues are now coming up in the forum. So, we can take up those questions and then discuss in the subsequent sessions. Thank you for joining this course, and I hope you will like this course. It will be helpful for your future studies, as well as if you want to go into research in any one of these if you are in chemistry, if you want to do the research in interdisciplinary biological world, then you can utilize your knowledge, and that will be, I hope that will be helpful for your future studies. Thank you.